more complex your data is, the more overlapping. Now what I was trying to do was find a full MS1. So, and this might not be a good example because it's pretty low amount injected, but the more complex things are, the more overlapping peptides you're going to have. Okay, so if you have more overlapping peptides, you're going to have overlapping multiply charged envelopes for those individual peptides. What the APD algorithm allows you to do is it allows the instrument control software to work together with some of the filters to figure out what the charge states are of those overlapping peptides. Okay, so in older software versions, it wasn't sophisticated enough. For older Orbitrap versions, it wasn't sophisticated enough to pull apart those peptides and figure out what the charges were. So it classified them as a unknown charge state. So that's why we have this setting, which was default 2. So when we fragment our ions to get MS2 information, if it cannot determine the charge state, it's going to call it a doubly charged ion and fragment it when we do our DDMS2. So even though I say 35% normalized collision energy, it uses the charge information when we say collision energy, this is normalized to the charge state. Okay, so if it knows that it's a 3, a 4, a 5, or a 2, it's going to apply HCD collision energy, which is normalized to the charge state. If it could not figure out what that charge was, it would call it a 2. Okay. So
I have a question.
yes, sir.
So here I saw like the energy, right? So for example, like this is for the proteomic research. We may not have a problem on the collision energy.
Yep.
For some,
What would the tune contain? What vital information for our mass spec would the tune have?
tune, right? Tune, I think we check the signal stability first.
What was the main thing we did? What was the thing that took the longest time yesterday? Calibration.
Yeah.
So the tune file. So there's a master cal file associated with it. Now this, before you would pull in the tune file that had the calibration file as well as the ion source settings. So now we're importing just the ion source settings into the method, and the calibration runs in the background. Okay, so no more tune file. Okay. In the ion source properties, we have the voltages, the heat, the ion transfer tube.
We will copy
and
from the tune method. Right?
Copy and paste it into it. Yep. We can also add our fames in here if we want to. We can add our fames in, and you have to have the fames installed to do that. So right now we don't have the fames installed. So that would mean installed physically on the instrument. Okay? That's the global parameters. Okay? And then also you have your application mode, small molecule, intact protein, peptide, method duration. All right, so now let's walk through these. So full scan. So yesterday what we did is we built a method based on a template. And we used from here, T stands for template, pretty simple. And we have all of these different things to choose from. And we talked about the different ones a little bit ago. We started with the general ID method. And I like to start with the high load and low load. And we grab the high load method. So let's let me get rid of this. Okay, leave it with that. So let's walk through each of these, and then I'll bring a brand new one and we'll set it up. Okay. So in full scan properties, let's walk through this. So let's just say we dragged over that ID one with the high load. In favorites, okay, if I say, so when you're building new methods, sometimes your scans will look like this, and basically it's giving you just the basic information. It's only giving you the Orbitrap resolution, the RF lens amplitude, percentage, and the polarity. Well, that's not enough. That's not enough for somebody who really wants to get in here and build methods. So I always go in and I show all, okay? You can also enable. You can disable or enable the recommendations. You can also enable the favorites. So I disabled that so that when you open it up, it should always bring up all of those advanced settings. And then if I go back and I say enable favorites, so that means you can flip back and forth. So I tend to like to just disable that, and it'll always bring those up. It's up to you how you want to set it up, but I like to see everything I can possibly see. All right, so full scan. So we have our resolution settings. We have 7500, all up to 48, all up to 480,000.
Pull up the table there.
Yeah, that's what I'm gonna pull up. Right. I always like to have my table up when I'm talking about this. And if you like, if they let you tape things on the wall, it might be a good thing to go up on the wall. But I'll give you this slide deck so you can always go, okay, we're done here. So I can just tell Norm we're done running. So resolution and scan speed, transient length. I'm going to pull something else up because this slide deck, I'm going to give you one of these. I'm going to give you the 240 slide deck as well. I feel like when they made this slide deck, it was a little bit rushed because this goes into a little bit of a opening segue about nominal mass versus exact mass. It just kind of shows you what you get with resolution and mass accuracy. So I'm going to give you, even though it's for the 240, I think it's nice to have this slide deck, and I'm giving this to my customers free of charge. This other slide deck because it walks through these, and for your new students that are coming through, this might be really good because it basically explains what the difference between low resolution and high resolution is. And what are we really getting by doing that high resolution? We're actually able to pull apart very closely related substances. And I like it because it goes through some of the definitions of accuracy, theoretical mass, all that stuff. And basically shows you the ability, shows you some of these abilities.
Yeah, it's really good for
it's really
giving lectures to students.
Exactly. So I'm going to give you that. It's really similar. It's a different instrument. The rest of it is pretty. The rest of the slides are pretty much the same. I'm gonna give you the slide deck just so you have it.
Yes.
I'm thinking of making my own, but it has to get approved. So with these resolution settings, these allow us to pull apart more and more closely related species. For proteomics, I mean, I wouldn't even run at the 408,000 to be quite honest, unless you're doing intact mass work where you really need that resolution to get that fine isotopic structure, or you're doing small molecule or metabolomics. But typically for proteomics, I live between 60,000 and 240,000. 60,000. I mean, you paid a lot of money for an Orbitrap Exploris, right? So I would run the 120 and 240 for your MS1s. Okay. And we did do that here. So we set it up for 120,000. But with that, remember, so to do our scan, okay, so to do a MS1 at 256 milliseconds, followed by let's say 20 MS2s at 15,000. So if we do the math there. So if we do 15,000, so if we do, I always like to do this just to show, if we do, so it's 32 milliseconds. 32 milliseconds times 20, that's 640 milliseconds plus 256. So that's 896 milliseconds. So it's close to a second to do all that stuff. Okay. So what we're trying to do when we're building these methods is balance the scan matrix, scan filter, scan header, so that we are getting a lot of scans across the peak, and we're not overdoing it. So you can see if we go to, because your instrument can do 480,000, it's not wise to choose to do 480,000 because it's going to take you over a second just to do the Orbitrap scan.
Yeah.
Okay? But we don't want to do low resolution for a full MS1. Even though that's nice and fast, our ability to resolve ions, and we want really good MS1 data. So when we're doing our MS1, let's see if we can open this now. It might be mad. Yeah, it's not going to open it because I have it open here on Freestyle. Now let's try it. Really? Sometimes it likes to do that. Let's go back to... So Qual Browser is no longer available on here, if you notice. So you have to go to your data. So let's go to your D drive. Where's your
Qual Browser, right?
Yeah.
I already built on the desktop.
You put it on the desktop?
Yes,
Smart
it's
man.
easier for me.
Smart man. There it is. And then sometimes you have to close it and then reopen it. Alright, so there's your mountain of data there, right?
Look at the shape. I guess
Yeah.
it's because too much loading. Right?
Yeah, it probably
I
is
can
too
try
much
later,
loading.
yeah.
You can try to reload. You can try to load less.
Yeah.
But
this one sample, I think, is normal.
exactly. But it I forget what I was wanting to show you in here now. But
Yeah.
so are these.
Yeah, then just
Oops, no, I didn't want that. I wanted. Sorry, I hit the wrong button. I'm gonna make it mad. I wanted. Okay, well that looks like an intact. That looks like undigested material there. So you've got data. I want to search it and see what it looks like. But you've certainly got peptides, and you've certainly got material that we can look at. It's just a matter of what it's going to look like when we search it. But anyway, that's good. That's good. Let me just go to the full MS. I just want to see what kind of MS2 you got. And to do that, I like to go to ranges. And I would recommend for you to get this, we want folks to migrate to, we want them to migrate to doing, want that, ranges, really slow. I like to get rid of all the scan filters and just look at, I call it the MS all.
Yeah.
And because that gives us our MS1 and MS2. Pin the bottom here. I mean, it's doing a lot of MS2. I'm just trying to find an MS1. Okay, so there's a lot of information there. So it's going deep into that. So MS1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 26, 27, 28, 29, 50. I can count. 51, 52, 53, 54,
Oh, wow.
55, 56. So there's a lot of MS2 information.
Yeah, because I mean, this is a really complicated
It's
sample.
really
yeah.
complicated. So we're going to do our first MS1 scan at 120,000 resolution. We're scanning over the range of 350 to 1500. Amplitude of 40% RF lens for our amplitude. And we did our AGC target at 300%. So we're filling with, remember, 3 million ions. So if I hover over this and I go to learn more, it tells us what our target is. So back on your LTQ, you set this up based on total counts. And here we use it as a percentage. We do a normalized base percentage. So we're setting it up to do 300 ions in for MS1. 300 charges, 300 ions. Sorry, 3 million.
Yeah, 3 million.
Yeah, 3 million ions. Excuse me. So this is basically going to fill, the ion routing multipole fills until it reaches the ADC target or the maximum injection time. The MS then transfers the ions to the Orbitrap for analysis. But before it goes to the Orbitrap, where does it go?
Before going to the
Before
C-trap.
it goes to C-trap first. So it has to cool them down, change their direction, and then push them specifically into the Orbitrap. Okay? So it's going to take us, so while we are scanning in the Orbitrap, okay, so we're doing our first scan in the Orbitrap here, our MS1, and as soon as that is done, as soon as that nears its completion, our packets for MS2 that are going to be isolating, accumulating, fragmenting, and then going into the Orbitrap one by one, set by set. Okay, so I just wanted to clarify that. All right, so we set that for normalized ADC percent target to 3 million. We set our maximum injection time of auto. So what does that mean? 300%, 3 million ions. It means that the split lens our split lens here around where the independent charge detector is, as soon as we're going to count our ions, our flux, and this is going to ensure that we're getting 3 million ions here in IRM for our MS1. As soon as we reach that target, the split lens changes polarity and snaps shut, and we no longer pull any more ions in. So we're letting it choose what it is. On the flip side, if we had a low level sample or a low protein amount, such as in maybe a single cell application or something like that, we might want to let this go. We can either let it go auto until it's full, or we can customize how long we leave that open. So, and to me, it's like a race, whichever one wins. But we're setting that to auto, and I would actually prefer to set it to auto. MIPS. You had this in the LTQ. We took this away during with the Q exactives. We called it something different. But they brought it back and called it MIPS again, monoisotopic precursor determination. And this is basically, it's going to filter your data, and it's going to ensure that we are determining what the monoisotopic mass is. So if we look at our, let me find the MS1 here. Might take forever. Okay, so if it looks at an MS1, and it's going to ensure that when we're looking at this spectral data here, it's going to ensure that when we are fragmenting, for example, on these peptides, we're going to ensure that when we're fragmenting, that it is picking the monoisotopic precursor based on the isotopic distribution, of this. So it's going to look at this distribution, and it's going to say, okay, I know that peptides have carbon, hydrogen, nitrogen, and oxygen, and it's going to say, do these peptides that it finds match that of a typical peptide based on its isotopic distribution? Okay, so it's going to prefer to fragment things that have a distribution that matches a peptide, so that it prefers to fragment things that have that are our peptide base. It's also going to help us determine the charge state and the most intense ion in that cluster. So we want to have that on because we want to make sure that we're determining the monoisotopic peak, and that we're going to prefer to fragment ions that basically meet the criteria of being a peptide. But we also have the option to relax the restriction of that preference when there's very few precursors. So if the data is if the sample is very dilute or weak, or we're not seeing many things that match that peptide criteria, we can choose to click this button and relax that restriction so that we can go after more and more precursors. Okay, so there are some intensity threshold is basically what it means. It's when we trigger. So we did a full scan event. Now we're applying these filters on top of it. So now we did the MIPS. Now we're going to go based on intensity. Intensity is basically when we look at the peak, how far up from the background are we going to fragment on? Okay, so are we going to make this value very low and trigger on every little peak that we see here in the background, or do we want to up the intensity so that we trigger on something that is more relevant to us? Okay. And there's a couple trains of thought. Now, if you're missing things and you have you want to go after low-lying peptides, you may want to drop this threshold. If you're picking up too much garbage from the background, you may want to make this higher. And then even in some circumstances with TMT, folks like to trigger a little bit higher up. And the reason being that folks might want to trigger a little bit higher up is if you fragment here versus fragmenting here versus fragmenting there, okay? If you think about the intensity of the precursors, your intensity of your precursors is going to be a lot higher here than it is here versus here, okay? So this is going to be highest, medium, lowest. But remember, it's always a game, right? It's always a game. And if we wait and trigger here versus trigger here, then we may be missing peaks underneath of this that are lower intensity, okay? So we may be ignoring things. So if you want to go deeper into your data, you may want to only choose to trigger at the lowest intensity here at this 5,000, so that we can go deeper into this data and find more peptides, find more proteins, okay? So it's a game, okay? It's a game, and there's always a trade-off. So those are my thoughts on intensity threshold. I like to keep it at 5,000. 5,000 is sort of the starting intensity threshold. I'll often bump this up to 8,000, 10,000, 20,000, depending on what I'm doing. Charge states. This is another exclusion filter or inclusion filter. We're only going to trigger on peptides that contain specific charges. And I set these for +2s and +6s. I'm sorry, +2s through +6s.
So for the top down, I think we'll see like 12, 15, right? So
and you would change that.
So then you change it, right?
You would include those other wider charge states. Now there's no sort of limit on that. You can go 1 to 100. Well, there is a limit, 100. One thing never do, ever, never include undetermined charge states for what you're doing for proteomics, because then it's going to fragment on all of those question marks,
yeah.
which are going to be for trash data, because you already have APD on. It's going to know what these charges are. So I would recommend
just keep this
your APD on, include the charge. You can go up to 7 or 8 if you want, depending on what kind of peptides you're getting. But typical tryptic peptides, 2 to 6, are what you're going to see, and I can show you that.
So it will increase it must increase deconvolution time, right? Because
exactly. All right. That's that. And we have dynamic exclusion. So, if you recall how to set this up on the LTQ, this is a lot easier, right? So you're not building all of those data dependent windows like you had to before. It's actually a lot more streamlined. So your dynamic exclusion ties in with everything we've already been talking about. So you can do an auto and just let it figure it out for itself, which I don't recommend doing. What I typically do is, depending on what you're doing, for a typical proteomics experiment, I look at my peak widths of the nano LC resolved chromatography, and I would look at the peak widths. So for example, in my data here, I would actually go in and I would look at the baseline, the base peaks, and the MS1, the base peaks, and look at my peak widths. Where is my mouse?
So when you're looking for MS1, you just look at the large peaks, right? I guess.
Yes.
Right. So
Yeah, there we go. So if I go in here and I look at, for example, if I go to ranges, wow, is that slow? It's mad at me because I'm not using freestyle. So if I go to base peak, that's my analogy for the exclusion duration.
Yes.
You don't want to be fragmenting the same peaks over and again because you're not going to get any valuable information out of it.
Yeah.
So we're going to wait. So if it fragments here, and we know that this peak is 20 seconds wide, okay, it's going to hit the threshold and it's going to wait an additional 20 seconds. I'm sorry, it's going to wait 20 seconds plus another 20 seconds to meet that exclusion duration before it triggers on that same peptide again. Okay? So that opens us up to find more peptides underneath of that peak. Because that peak isn't just one peptide, it could be hundreds of peptides. Okay? So our exclusion duration. Now where are instances where we break my rule of thumb? We break my rule of thumb if we're going to do things like low-level proteomics, or we're going to do things like single cell. Okay?
Yeah.
So if we're doing single cell proteomics, we may want to actually triple this value. So 60 seconds, perhaps even quadruple, 40 seconds. So to find more and more peptides, or more and more proteins, we're going to make that go longer. On the flip side, we may want to make this shorter than the 2 times peak width designation. There's a reason for that as well, because if we fragment here at the bottom of the peak, as we reach our threshold, if you're looking for structural information, post-translational modifications, we want to get really good sequencing and figure out if we have post-translational modifications. It's not a very complex sample set, so you're doing phosphoproteomics, something like that. We may actually want to trigger to do the identification, and then shorten that exclusion duration to maybe 50 to 60% of the peak width, so that we fragment again
Right there,
somewhere up there.
Okay, I got it.
So you understand why we would want to do that, because remember, the intensity of the precursors
Yeah, when you increase
is
it.
going to be low here, but if we trigger it again somewhere on either the apex or on the downward slope of that MIPS gives us, and try to fragment on the main monoisotopic precursor, we're going to exclude other isotopes of that.
Yep.
We also have the option to check or uncheck, perform dependent scans on single charge state per precursor. So when checked, only a single charge state will be analyzed for a given analyte, after which all states will be added to the exclusion list. So remember, you have your peptides that can exist in multiple flavors, depending on where they cut. You have a long peptide that can multiply charge. Okay? So if we do this, it's going to, when checked, only a single charge state will be analyzed for a given analyte, after which all other charge states will be added to the exclusion list. So if it's checked, it's only going to do one. So we left it open.
Yeah.
Okay.
Yeah.
So different applications, ETD, HCD, different charge states are going to fragment differently. It gives you just more richness or more possibility of identification. Okay. Is that clear?
Yeah.
Okay.
Yeah.
Cool. Let's see what Angelita's up to here, and maybe let Norm jump in. I think Angelita would like to get up to lunch. Let's see. The last bit of this is your MS2. Actually, there's 2 more pieces to this. the MS2, we have the ability to select all of our parameters here, starting with our isolation window. So now remember, we go back to our quadrupole. Quadrupole is going to select. So first thing off the bat, we're going to select our mass range for our MS1 here. We're going over a wide range, 350 to 100. MS2, once we identify precursors from our MS1s, it's going to start building, it's going to start isolating precursor one by one by one by one, okay, for fragmentation. We have the ability now to decide how tightly around that mass range, or that mass, we want to isolate. Okay, so 1.6, we can go all the way up to like I have a chart here. It can go up to like 2 or 4 isolation windows. So and you remember, with your isolation window, you're going to split this in 2. So if it's isolation window of 1.6, it's the mass plus or minus 0.8 on each side. So it's 1.6 bracketing your mass range. So if we fragment this, if we choose to isolate this 429, it's going to do this 429.7447 plus or minus 0.8 Dalton per side. Okay,
It's pretty wide, yeah.
pretty wide. Now we can narrow this, or we can make this really wide. I prefer to kind of balance it out and do an isolation window of like 1.2, 1.6, so 0.6 to 0.8 around each side.
So does this number also affect how many MS2 we are going to receive?
No, doesn't affect how many MS2. It affects it's more or less going to affect the intensity of the ion. So if we make or the specificity of the ion. So if we make it really tight, then we're going to, if you infuse any peptide into the instrument and you make your isolation window really narrow, your intensity drops. Okay, so as we start to isolate more, we start to cut off, if we start to isolate more around a mass, then we're going to start pulling away its ability to transmit. Okay, so if we make it too narrow, we go really specific, and we don't allow things of other things that are unrelated out of this range through, so we can increase our specificity. So on a triple quad, if people are getting matrix effects or unrelated substances kind of co-eluding with them, you make this really tight around those masses to abrogate those other contaminants. But for proteomics, we want to kind of make this a little bit wide and allow the instrument to do its job, because basically when it fragments and identifies, you have high quality full scan data at high resolution, followed by lots of lower resolution MS2 scans. We leave this number somewhat wide to allow everything through, and then we let the mass spec do the work. The mass spec is going to fragment and do the work. Okay? So again, my rule of thumb, on the tribrids, I would say, on my tribrid customers, I recommend you go no lower than like 0.7. It's the same quadrupole. I would recommend you go no lower than 0.7 on this value.
Because this is under in the low resolution.
Right. This
So,
is on lower
so
resolution.
we have like 10 ppm primary scan, right? Accuracy, I think. And then what would be the second, the MS2? What do you think is the accuracy of MS2?
Oh, accuracy of MS2 is going. These are all going to be 1 to 3 ppm mass accuracy.
Okay.
So yeah, you should be fine, and especially if you're using a well-calibrated system or an internal calibrate, maybe 1 or sub ppm mass accuracy. Other things you can do, you have an isolation offset, and this would be more for, you're going to be doing isolation offsets when you're doing labeled species. This you can shift, so you're going to isolate the window around that mass, and then you can shift it one way or the other. Okay, so you can use a positive or a negative isolation offset. So you'd be taking that 429.7447 plus or minus 0.8 on each side, and then that isolation offset would be another little fudge factor that you can move it even further. Okay, so this is commonly used in our Sherquant assay where we have internal standard triggered PRMs. So we basically trigger our PRMs based on identification of the internal standards, and then we use this offset to target product ion fragmentation on our unlabeled peptides relative to the labeled peptides. So some folks like to use that for other applications, but I typically use this when we're using labeled peptides and unlabeled peptides. Talked a little bit before about collision energy mode. We have fixed or stepped. So we talked about how you can use step for your small molecule applications. We also have this normalized and absolute. I would recommend you use normalized at all times. Absolute is just fragmentation energy applied in the HCD cell. So remember, our HCD cell is also referred to as the ion routing multifold. This is where all the fragmentations happen. So as it goes in here, what we're doing is we're changing the bias of the energetics for the movement of the ions in here. So basically we're creating a profile by which we are causing the ions to move faster or collide. Or if you want to be morbid about it, it's like how deep is how far is the cliff ledge versus how far our victim falls. So we make this really steep, more damage is done. We make it really narrow, we make it really shallow, less damage is done. So we're creating like an energy well here for something to fragment. So when we do that, we do it, but we also do it, our collision energy based on absolute fragmentation and normalized. For proteomics, we want to do it based on normalized collision energy because we're normalizing it to the charged state. We're going to get the best fragmentation for our peptides if we normalize our collision energy based on the charged state. So always want to run it in normalized mode. Collision energy, again, 30 to 35% for proteomics applications. You might want to bump this up a little bit when we talk about TMT. 30 is sort of my sweet spot. I like 30 and 35. For TMT, you might want to run up to 45, 55. We'll build some methods for that. The balance is we don't want to under-fragment it. That's the thing we're trying to avoid. Orbitrap resolution in the MS2. So let's go back to my chart. All right, so we talked about the MS1 full scan. We ran at 120 resolution. It takes 256 milliseconds to spin it back and forth to separate those ions. But when we do our low resolution MS2 scans, and I would recommend playing with 7500 and 15,000, transient lengths are 16 and 32 milliseconds. That's how long it takes to do. Balancing that with high resolution MS1. And when it does the database searching.
Yeah. So the guy who worked initially on our Orbitrap.
Yeah.
So he didn't like this idea at all.
Oh, he did?
Yeah. So we always run like MS2 at high res.
Oh, you did? Okay.
Because, but I don't know. But I'm not convinced it's.
You can. I mean, you can. I mean, you could run.
And we had like always complained that our spectra. I mean, our number of proteins was like low.
That's what's gonna happen.
But I'm not convinced if you have more proteins, it's meaningful. Yeah. You know. So that's
you can always run
yeah.
at higher resolution
and
then build exclusions.
I mean, but we can try. Yeah. Of course, yeah.
But I mean, 15. That's why.
But that's what usually people do, right? 15. Yeah. That's what.
I like 15. I mean, you can go 7,500. It's going to give you more, but it's going to let through a lot more.
Yeah.
But you can always look at the quality of that data when you when you pull up your MS2 data in Proteome Discover. You can look at the accuracy, and the accuracy of the instrument is still pretty darn good.
Okay.
So we can take a look at that. But again, it really depends on what your overall goal is. But 15,000 resolution is what I would recommend for MS2s. You can go to the 7,500. Honestly, to convince yourself when you're running this on Gila or whatever you're going to run, I would often set it up to do it in one mode in two different resolution settings, and just see does it give you more protein IDs when you go to the lower resolution? Does it give you less when you go to the higher resolution? does it give you better
Yeah, we can-
accuracy data?
Yeah.
So you can design the experiments here,
Yeah.
and, run them over a weekend, and get some good data on it. I'm gonna skip this turbo TMT right now because we're gonna come back to that. This first mass is this scan range mode, define first mass. We use this to designate when we do our MS2s. What do we set as our boundary for the MS2? What the data we're going to collect? We can say auto and just let it generate whatever it wants, and it's going to drop and go as low as it can go. So if we set so for MS2, if we set this to auto, it's going to go all the way down to 50 and try to do it. So what I like to do is define your first mass of 100 or 110,
Yeah.
because then that way everything is kind of uniform. Okay? All right. And then last but not least, which I believe are some of the most important settings in the software, are our AGC targets for our MS2 and our maximum injection time for our MS2. Why is this critical? Again, back to the drawing of the instrument. Remember what we're doing. We've done our full scan in high resolution for our MS1s, and that is going to set up what masses we're going to fragment for product information in MS2 for not only structural ID, but also for protein identifications based on the peptides. So we want to make sure that we fill the IRM with enough ions to give us quality MS2 spectrum. Okay? And again, we also don't want it to be too many. We don't want it to be too few.
Yeah.
Remember, we're balancing coelution or basically the coalescence of peaks with the ability of not seeing stuff. So, AGC target. So here we just said we designated it as a custom. So we have the ability to go standard, or we have the ability to do a normalized AGC target percent based on that value. So we know based on the instrument, normalized based for MS2 scans in Orbitrap is 1E5. So 100,000 ions. Okay. Do we want to? We can go beyond that, or we can go above that. I would recommend we either do standard and do it at 100%. We do it at 100%, which is 1E5, or we do custom. So if I go back, if I click standard, and then I come back and I go to custom. Sorry, custom. It gives me the normalized ADC percent of 100, because that's the default. So they're going to get 100,000 ions charges. We set it at 75, and what I recommend is setting it, 50% or 75%. So we're getting basically 75% would be 75,000 ions, 50% would be 50,000 ions, and just take a look at the data and let the data steer you as to what the best settings are going to be. So what we can do is take a look at that. So now the caveats here are, if you want to ensure that you've got enough ions, you can set this a little bit higher for low intensity populations. If you have a high amount of peptide or protein digest, you can set this on the lower side. That's why I set this for 75%. Okay. Along with that, we also have our
That
maximum.
means if we want, for example, a single protein, and we can go higher.
Go higher.
Yes.
And you can go higher on that to stack the deck in your favor. And then likewise, for the maximum inject time, okay, so maximum injection time, we want to be wary of our transient length. Okay? So our maximum inject time, remember our transient length here, it takes for 15,000, it takes 32 milliseconds to do the scan. Okay? 32 milliseconds to do the scan. So we typically don't want our max inject times to be too much higher than this value. Okay? So we want this to be, within 10 milliseconds of that. So I actually set this to be a little bit higher. So you can do auto and let it figure it out for itself, okay? Or you can do custom and set it based on your transient length and use your table. So if you wanted to be in sync with your Orbitrap,
So it's seconds, right? Yes,
Yeah.
it's milliseconds. Yeah. Okay. Okay.
if you wanted to be in sync with your Orbitrap and
So
make sure that we're
yeah.
not wasting any time,
Yeah. Yeah. Okay.
you
Got it.
want your max fill time, max injection time, to be about 10 milliseconds lower than your transient length.
Okay. I
okay.
see. Okay.
That way it's not wasting any time. If you want it to go a little bit longer, then give it longer to fill with iron, longer to accumulate. So you get good quality, good quality, high quality spectra, or high number of spectra. You can go longer. And as we get into the applications where we're looking at low-level proteomics or single cell, that's a key figure because we're going to crank that value up. We're going to let it accumulate for longer and longer and longer. Now it's going to cut down, it's going to screw up sort of our scan matrix because it's going to cause our fill time to exceed our transient time. But remember, for those applications, we have a different goal. And we're trying to identify something and trying to find more proteins in a sample that is very, very dilute.